So, at the first part of our lesson, we have considered how an RSA algorithm works and explained why do we say that the security of RSA algorithm depends on the integer factorization problem. Actually, that version that we have considered at the first part of our lesson showed how to use this open key cryptosystem for confidential message transmission. However, as we said before, this type of cryptographic protocols can be used for key distribution and digital signature as well. Actually, the asymmetric cryptosystems are used for key distribution and digital signature, since for confidential message transmission we can use symmetric key cryptosystems, which are more fast algorithms than the asymmetric ones. Since, as we saw in the example of RSA algorithm, we need to generate a key and do some calculations which are quite expensive. And although there are some algorithms for fast exponentiation, yet these algorithms work much slower than the symmetric key algorithms. Before we start learning key distribution protocols and digital signature protocols, let me show you one more public key cryptosystem which is also based on discrete logarithm problem. This is an Elgamal message transmission protocol. In this protocol, we work on a prime finite field FQ. So Alice chooses some field FQ on which the encryption process is done. Then she chooses an integer b and computes y, which is equal to g to power b. This element g of the finite field FQ is chosen so that g generates this field FQ, and we know from our lecture on the finite fields that an element g is called a generator of a finite field FQ if by writing this element to powers from 0 to q minus 1, we can obtain all the elements of which this finite field consists. So the Alice's private key is this power b, while the finite field, the generator, and y are parts of the public key. To send an encrypted message to Alice, Bob chooses some random integer key, and using the private key of Alice, he computes a number x, which is the power key of the generator of our field, and computes the ciphertext, which is a message multiplied by y raised to the same power key. And unlike the RSA algorithm, he sends to Alice this pair x and c. To decrypt a message, Alice multiplies the received ciphertext c by the received number x raised to power minus b, which is her private key. We know that the ciphertext c is equal to m multiplied by y to power key, and this x was calculated as the generator raised to power key. So, if we substitute these values of c and x, we obtain this expression. So, on the other hand, from the key generation algorithm, we know that this y is equal to g to power b. So, we have g generator raised to power bk multiplied by the same generator multiplied to the power minus bk, which results in 1, so we are left with the message alone. So as a result of decryption, we obtain the encrypted message. So to see how it works, let us consider an example, and this time we are going to work with really small numbers. So suppose that we are working in the field F7. So the elements of this field are 0, 1, 2, 3, 4, 5, and 6. We choose this G number, a generator, as 3. So now let us check the validity of our choice. We raise 0, 3 to power 0, 0 and obtain 1. 3 to power 1 is equal to 3. 3 square 9, which is equal to 2 modulo 7. 3 to power 3 is equal to 27, which is modulo 7 equal to 6. 3 raised to power 4 is equal to 81. Modulo 7, this is 4. 3 to power 5 is equal to 243, which is modulo 7 equals to 5. And finally, we have 3 to power 6, which is 729. Modulo 7, this number gives us 1, and we know that this result was the expected one according to Fermat's Little theorem. So we have just validated that 3 is a generator of the field F7, and we can actually choose our G to be 3. So now let us choose our private key B and let it be, say, 5. So now if we calculate our Y, which is equal to this generator raised to power B, then we obtain 243, which is equal to 5 modulo 7. So we have generated our public key, which is equal to 7, 3, and 5. And our private key is also equal to 5. So with these calculated keys, we are ready to encrypt and decrypt a message. So now suppose that Bob wants to send a message to Alice. For simplicity, let this message to be equal to 2. Also, he needs to choose some integer k. Let k to be equal to 3. So we calculate x as a generator of the field F7 to power this chosen integer key 3. So 3 to power 3 is equal to 97, which is 6 modulo 7. Now we are ready to calculate our ciphertext, which is equal to message multiplied by y to power key. Our message is equal to 2 multiplied by y is equal to 5 to power 3, which gives us 125 multiplied by 2 is 250. Modulo 7 250 is equal to 5. So Bob sends to Alice the pair 6 and 5. To decrypt the ciphertext, Alice takes 5 multiplied by 6 to power her private key, which is equal to 5. However, in the field, we cannot raise an element to the negative power. Therefore, we will make use of Euler theorem, according to which a number raised to power phi of r is equal to 1 mod r whenever this t and r are relatively prime. We know that 6 is relatively prime to our modulus 7. So we can multiply this expression by 6 to power phi of 7, which is equal to 5 multiplied by 6 minus here minus 5. Phi of 7 is equal to 6. So we have 5 multiplied by 6 to power minus 5 plus 1, which is 6 itself. So we have 30. And 30 modulo 7 is equal to 2. So we decrypted our message successfully, and our message is equal to 2. as we said, the security of this algorithm transmission protocol relies on the discrete logarithm problem. So, now let us consider how a public key cryptosystems can be used for key distribution protocols. The general description of a simple key agreement protocol includes several steps. First, Bob constructs a public key encryption scheme and sends his public key to Alice over the unsecure channel. Alice generates a key for symmetric key encryption scheme, and then she encrypts this key using Bob's public key and sends the encrypted key to Bob. Bob decrypts using this private key and recovers the key for symmetric encryption. So, since Alice herself generated the key, no one else knows this key for symmetric key encryption scheme, and since only Bob has his private key, only he can decrypt this key, and Alice and Bob can begin communicating with privacy using the symmetric key system and the common shared key. So in this scheme, as you can see, as a message in public key cryptosystem, we actually use a key of a symmetric key encryption scheme. And the RSA protocol that we have already seen in the first part of our lecture can actually work within this protocol. Now let us consider another example for a simple key agreement protocol. This protocol is called a Diffie-Hellman key exchange. Diffie-Hellman key exchange algorithm is also based on digital logarithm problem. So we work with a finite field G and its generating element G. So suppose that Alice and Bob want to agree on a key for symmetric encryption scheme. So they agree on a finite field G, and Alice picks a random number A and calculates x, which is equal to the generator of the field raised to power of this number A. Bob also chooses a random number B and sends to Alice the number y, which is equal to the power B of the generator of a finite field. So Alice, upon receiving this y, computes y to power A, and Bob computes x to power B, and by doing this they can easily share a secret key. Since the values of G to power B to power A and G to power A and to power B are same because our finite fields are power associative. So if we show this key agreement protocol using schemes, we are going to have the following picture. So Alice and Bob choose the field on which they are going to work, which means that they choose the prime number for a prime field. Then they choose the generating element of this field. Alice selects a number A and Bob selects the number B. Alice calculates G to power A modulo P, since we are working in the field FP, and sends it to Bob. Bob calculates G to power B modulo P, again since we are working in the field FP, and sends the result of this calculation to Alice. And since power is an associative operation in the field, we have the same key shared between parties. So again, let us see how it all works. So suppose that Alice and Bob agreed on choosing the finite field F17. So our P is equal to 17, and suppose that as a generator they choose the number 2. Now both Alice and Bob need to choose some natural numbers A and B. So suppose that Alice chose her A to be equal to 5 and Bob chose the number 11. So here we need to calculate 2 to power 5 mod 17, which is equal to 15 modulo 17. So Bob calculates the value of 2 to power 11 modulo 17, which is equal to 8. And this 8 goes to Alice. So Alice takes this number 8 and raises it to power A, which is her private key. So we raise 8 to power 5, which is equal to 32,768. And modulo 17, this number is equal to 9. Bob received the number 15, so he takes this number 15 and raises it to power 11 and calculates it modulo 17, which is also resulted in 9. So this 9 is further used as a key for symmetric key cryptosystem. And this is how the Diffie-Hellman key exchange protocol works. Next, we consider how to use public key cryptosystems to digitally sign some document. But before, let us define what a digital signature is. So, digital signatures are a very effective mechanisms used for authenticity and non-repudiation of messages. That is, by digitally signing a document, we authenticate ourselves, and at the same time, later, we will not be able to deny sending this message. Actually, this type of algorithms may be further expanded to be used in the manner so that authorities cannot figure out the sender's identity. But in this course, we are going to consider the classical digital signature algorithms. The basic idea behind the digital signatures are quite simple. So we know that in open key cryptosystems, the public key of parties is always available. So to sign a message, a signer uses its private key and generates a signature. And to verify that signature which was used to sign a message M, we can use the signer's public key. And since the message is signed using a private key, no one should be able to generate a valid signature other than the holder of this private key. So let us consider how digital signatures work on an example of RSA algorithm again. If Alice wants to send a signed message to Bob, she encrypts a message in an ordinary way using Bob's public key, which are denoted by N with subscript B, which stands for Bob's, and E with subscript B as well. So, to sign this encrypted message, Alice uses her own private key DA and raises this ciphertext to power DA and does the calculation modulo NA, which is part of her public key. Bob can verify Alice's signature since he knows her public keys EA and NA. He can raise this signature which was received from Alice to EA, and we know that the signature is obtained using her private key. So if we substitute this value of S by C to power D, then we should obtain the ciphertext again, and Bob accepts the signature as valid if the result of this calculation, which is denoted by E1, is equal to the ciphertext which was sent along with the signature. So as you can see, signing a message with the RSA algorithm can be considered as a double encryption of the message. However, for signing we use our private key, since only we know the value of our key. Signing a message with the Elgamal algorithm uses the same logic behind, so therefore we will not discuss this digital signature algorithm in our course. So recall that when we were studying hash functions, we saw the message authentication codes, which could also be used as a signature in the message. However, if we use message authentication codes, we cannot guarantee non-repudiation, transferability, and managing keys with this type of algorithms. However, message authentication codes work faster than digital signature algorithms. So nowadays, all the cryptographic algorithms that we have studied so far are widely used. For example, let us consider the typical application of cryptographic algorithms, and if we look at the process of simple handshake protocol used to establish connection between the client and server, we know that the client and server must agree on various parameters to establish this connection. So the client requests a secure connection and presents a list of cipher suits which are supported by this browser. The server picks a strongest supported cipher suit and sends back his digital certificate, including the certificate authority and his public key. Then our browsers send a random number to the server by encrypting them using the server's public key. By doing this, the browser, that is a client, and the server generate a key material from this random number to establish a secure connection. This secure connection is established by means of symmetric key cryptosystems, and this key sharing process is done by using the public key cryptosystems. Graphically, this handshake protocol, which works within the secute socket layer, can be represented as follows. At the first phrase, the client and server exchange hello messages, where they establish security capabilities including protocol versions, session ID, cipher suit, compression method, and initial random numbers. That is, they say each other which cryptographic protocols they support. With the server hello, the server sends the certificate, the server public keys, and requests certificate, and by doing this, the server signals end of the hello message phrase. So at the third phrase, our browser, that is a client, sends certificates if this is requested by a server. At the same phrase, the browser generates a random number and encrypts it using the server's public key and also sends them to server. So at the phase 4, the server decrypts the obtained random string using its private key and changes the cipher suit, and by doing this it finishes the handshake protocol. After this, the random string, which was generated by client and sent to the server in the encrypted form, is decrypted by server, and this string is used as a key for the symmetric key cryptosystems. So as we can see, asymmetric or public key cryptosystems were used here just to share the key for symmetric key cryptosystems. This is done because asymmetric key cryptosystems always slower than the symmetric ones, and to establish a fast communication after the handshake protocol, symmetric key cryptosystems such as advanced encryption standard, and if there is some streaming, then some standard of stream ciphers are used for further communication. Now, the connection between client and server uses an encrypted channel. So, concluding our course, I would like to discuss why sometimes crypto fails. As we could see throughout our course, cryptographic algorithms are designed with taking into account many factors. However, sometimes it is possible to break ciphers. So, to explain why crypto fails, it is important to distinguish various issues. For example, it can be a bad cryptographic algorithm, or it can be just a bad implementation of a secure cryptographic algorithm, or bad design, and so on. Even with a good cryptography, adversaries can find the way around operating outside the model. And also, even with the best cryptography, there can be some other weak points elsewhere in our system. Since when we talk about information and communication system, these systems are very complex. So the cryptography is not a magic bullet. Since for the cryptographic algorithms to work correctly, it must be implemented correctly. It must be integrated from the very beginning when establishing the system, and not added on after the implementation. Remember that according to the basic principles of information security, the system is as secure as its weakest chain. So the crypto alone cannot solve all the security problems that our system can face, since there are key management issues, social engineering, insider attacks. So to avoid security problems, we need to implement defense in depth principle. That is, we need to implement our security at 4 levels, which are the physical level, the administrative level, the logic level, and the final one is the cryptographic suites to be used in the system. And always remember that security is not a product. We cannot just set everything and say that the system is secure. Actually, security is a continuous, regular process. So the system is as secure as its weakest chain, and in many systems, humans are considered to be the weakest chain. So we need to educate users about appropriate security practices as well. And finally, there are general recommendations to keep our system secure. And the first one states that we need to use only standardized algorithms and protocols, since these algorithms were investigated by the cryptographic community, and it is better to use these algorithms instead of designing our own. Since to start using some cryptographic algorithm, we need it to be evaluated by experts. Also, it is preferable not to use the same key for multiple purposes. Also, we need to be careful when choosing our cipher keys. So this was our last lecture on this course. I hope that the information given in this video was helpful. Thank you. Bye.